Alrighty, part 4 of our adventure into Riemann Sums. We're going to go ahead and run it all the way through this time without the preliminaries and actually find the actual area by applying the limit. Okay. Now remember that we get a Riemann sum by dealing with this sigma. Okay. But if we do it for in subdivisions instead of a particular number, we recognize the fact that this actually gives us a function, which in the past we've referred to as S of n. Okay? And so if I actually deal with this scenario and run it down and get an expression in terms of n, that function will give me any approximate area for this function on this interval for n subdivisions. So if I plug in 3, it'll give me the approximate area for 3 subdivisions. If I plug in 17, it'll give me the approximate area for 17 subdivisions. Okay? So what we're going to do is, instead of actually doing the numerical as a preliminary, that was the whole point of the last lecture, we're going to go ahead and jump right in. Okay? Now this function is a little bit more complicated because it's, first of all, it's got 3 terms, and second of all, it's cubic. But basically what's going on here is still the same sort of thing. Let me go ahead and show you that function. The function looks something like this. Okay, and I would love it if we had the time and we could go through the fact that you should actually know the shape of this graph based upon your previous knowledge in what we've talked about in terms of graph analysis and whatnot. But we won't. Okay. But suffice it to say that this is the area that I'm looking for from 0 to 3, right? And we're going to basically find the S of n for that. And then, as sort of foreshadowed at the end of the last lecture, the end of the last video, we're actually going to apply the limit in order to find the actual area rather than simply the approximate area. Now, I know that delta x is going to be 3 over n. Okay? And I know that x sub I, being a plus delta xi, is going to be 0 plus 3 over n times I, or just 3i over n. Now, when I plug that in, I know that S of n is going to be the sigma from I is equal to 1 to n of delta x. That delta x. So 3 over n, that is the width of all of the subdivisions. And then I need to know the height. Well, I have to take my x sub I and, of course, plug it into my f of x. So I have 1 plus, and when I plug 3i over n into this one, it actually winds up being really easy, but we'll go ahead and do it sort of one step at a time just to make sure that we're all following along. And I get 3i over n cubed. Okay. Now let's go ahead and simplify this. I think that's going to be welcome, considering the fact that it looks a little bit nasty right now. It's not going to get much better, but it will get a little bit better. So we have 9i over n minus, well, I'll tell you what. When I cube that, that winds up being 27, right? But the 27 is divided by 3, so it winds up being 9i cubed over n cubed, okay? Now, remember, the hard part is remembering when you have a construction like this to actually apply the cube to all 3 of the factors in there. And then the mistake that I made last time is remembering that when you distribute the 3 to also distribute the over n, okay? So let's go ahead and try to do that while we're talking about it. And you get 3 over n for that first term. You get 27i over n squared minus 27i cubed over n to the 4th. Okay? Now, we're going to go ahead, and I actually find it always helpful to go ahead and just split it up, like pull everything out that is not that is not an I, okay? Plus 27 over n squared, sigma I is equal to 1 to n for I, okay? And then minus 27 over n to the 4th, sigma I is equal to 1 to n of I cubed, Okay? Now, if you miss that, this term is here, okay? This term is here, and this right here is this term, okay? And of course, now we have the sigma in such a way that we can actually use our formulas now. Now you're looking at I cubed and you're thinking, oh, well, I squared was such a mess. I cubed, I'm sure, is an even bigger mess. Actually, I cubed is actually easier than I squared. I squared is the hard one. So 3 over n, that sigma just winds up being n. Okay, 27 over n squared, this winds up being n plus 1 over 2. And remember, I cubed is just this squared. So 27 over n to the 4th, you have n squared, n plus 1 squared over 4. Okay? So this is basically turning out to be a little bit nasty, but you know, it's not too bad. So these n's cancel out. One of these n's in the denominator cancels out with this one, so I'll just scratch out the squaring. This goes from to the 4th to the 2nd power when it cancels out with this one. Okay? And what I get here is 3 plus 27n plus 27 over 2n minus 27n plus 1 squared over 4n squared. Well, that's good enough, because now this, if I wanted to actually plug in for 4 subintervals, for 8 subintervals, for 16 subintervals, that would be just dandy, and I would actually get out the appropriate answer. But I'm not worried about that. I'm worried now about, okay, I want to take this, and what if I actually run the number of subintervals off to infinity? Well, we've talked about it before. The more subintervals, the better the approximation. And so if you run the number of subintervals off to infinity, you stop having an approximation and start getting the actual area. Okay? So if we take the limit as n approaches infinity, and we're just going to use our limit rules that we sort of have from our n behavior discussion. That's minus, not plus. 27n plus 1 squared over 4n squared. Now, as n approaches infinity, what happens to that first term right there? Excuse me. What happens to that first term right there? Well, that just goes to 3. What happens to the second term? Well, it has the same degree in the numerator as it has in the denominator, so that's 27 halves. And then this one has the same degree in the numerator and denominator, so we basically do the leading coefficients again, and that's minus 27 fourths, or 3 plus 27 fourths, once you simplify these fractions, right? Okay, well that's 27 fourths is just shy of 7, okay, so it's 6 3/4, so that's 9.75. That is the actual area under the curve of the function f that we're given, because I've taken a number of subdivisions and made them infinite. Okay? Now this is an insanely detail-oriented problem. And oh my gosh, if you had to do this every time in order to find it. Now thankfully, you've already been hinted at exactly how we're going to be doing it in the future. Anti-differentiation is basically the same thing as integration, and that's how we're going to basically wind up doing it. Okay, so let's actually look at, and I'm going to go ahead and introduce the notation for integration. If I have, and I'm sort of getting ahead of myself, but I think that y'all can follow along. This means the same thing as taking the antiderivative. Okay? Now, and instead of actually doing it, because I don't want to get ahead of myself too far, let's go ahead and I will basically, let's go ahead and do it on the front screen right here. If you go alpha f2, notice that it says function integration right here on 4. Oh my gosh, will you look at that. And so now I just have to pop this in. 1 plus 3x minus, and let's go ahead and do a proper fraction, x cubed dx. Oh my gosh, that's what we got. Isn't that just fabulous? Okay? And you'll understand exactly what this means here in a couple of videos, because we'll be getting into what's called the fundamental theorem of calculus. You need to go back and look at your notes from last year. We did a couple of examples of this. I posted more examples of this that you should have either saved the PDFs or printed them out and put them in your notes. I hope that you listened to me and didn't throw anything away. This stuff we've covered before. Okay, there's nothing that we've covered so far except for maybe midpoint Riemann sums that shouldn't sound incredibly familiar. So a lot of this should be review. So if you look back over your notes from last year and you watch all the videos and you sort of flip through the examples in the Stewart book, I don't think that 5.1 and 5.2 are actually going to be all that difficult for you. We're going to go on in the next video and we're going to talk about applying Riemann sums to when they give you tabular data rather than an explicit function, because they love to ask Riemann sum questions on the AP exam like that. And then I'm going to try, and in the last video, probably sort of sum up and try to apply how I've walked through 5.1 and 5.2 in terms of Riemann sums, and how it applies to the way that Stewart goes about it. Plug up the last few holes. So I think that we're going to round out 5.1 and 5.2 with a total of 6 videos, but we'll go ahead and see how that transpires. This isn't exactly the longest video. We'll go ahead and stop it here because I don't want to run over again. But be looking for the tabular stuff in the next video.